Let us start with the discussion on some other non-traditional optimization tool for optimization. Now, actually we have already discussed the reason behind going for the non-traditional tools for optimization. Now, we want some robust optimization tool which can tackle a variety of problems, and that is why the concept of non-traditional tools for optimization came, and to develop all such tools we take the help of our mother nature. So, these are all nature inspired techniques. Now, if you see the list, we have got a large number of tools. For example, say if you see, we have got the tools like genetic algorithm, which I have already discussed in details. So, let me just write down, we have got genetic algorithm. So, in short, that is known as GA. Then we have got the simulated annealing, simulated annealing, simulated annealing, in short this is known as SA. Then we have got particle swarm optimization, particle swarm optimization, in short this is known as PSO. We have got the tools like genetic programming, in short this is known as GP. We have got evolution strategies, in short this is known as ES. We have got evolutionary programming, in short this is known as EP. Then we have got ant colony optimization, ACO, artificial bee colony, that is ABC. Then artificial immune system, it is AIS. We have got differential evaluation, DE. We have got algorithm like cultural algorithm, in short CA, and many other like BAT algorithm and others. There are so many algorithms. Now, here actually what I am going to do, the principle of genetic algorithm I have discussed in detail. Now, I am just going to concentrate on at least two more algorithm. One is the simulated annealing, another is the particle swarm optimization, and I am just going to discuss their working principle with some suitable numerical example. Now, let me start with the simulated annealing first. GA I have already discussed, now I am going to concentrate on the simulated annealing. Now, simulated annealing, that is our topic 9. On principle, actually we are going to solve the minimization problem, and actually what we do is we try to copy everything from the solidification process of molten metal, and the solidification process of molten metal has been copied in the artificial way in simulated annealing. Now, let us see its principle. Now, simulated annealing was proposed by Metropolis et al. In the year 1953, long back, even before the introduction of genetic algorithm. Genetic algorithm was proposed in the year 1965, but the concept of simulated annealing came before that in the year 1953. Now, as I told that here we try to model the cooling process of molten metal in the artificial way, and we try to develop one optimization algorithm which on principle can solve the minimization problem. Now, this schematic view shows, so this is as if the molten metal, and this shows actually the solid state of the metal. Now, whenever a metal is in molten state, it has got high energy. So, this is in high energy state, and if you just cool it down, so this will become solid, and solid state corresponds to the minimum energy. So, from high energy I am just moving towards the low energy or the minimum energy. So, on principle I am solving the energy minimization problem. Now, let us see how to model it in the artificial way, and we can develop a tool for minimization. Now, if you see the metallurgy, now during this particular cooling, if I consider a high speed of cooling or the rapid cooling, I will be getting a special type of crystal. But if I use the slow cooling rate, I will be getting different types of clusters. So, let us try to investigate that first. At high cooling rate, the molten metal is converted into the polycrystalline state. On the other hand, if I just go for the slow cooling rate, so I will be getting a single crystal for this particular the metal. But the fact is, if I compare the energy level of this crystalline state, that is the single crystal state, and the polycrystalline state, the energy level of the crystalline state is much lower compared to that of the polycrystalline state. So, during this particular solidification, our aim is to go for the single crystal state, so that we can get the minimum energy state, and that is why we go for the slow cooling. And the method of slow cooling is nothing but the annealing. So, by annealing we mean the method of slow cooling of molten metal, and this particular process of slow cooling or annealing has been modeled in the artificial way in the form of an optimization tool. So, I am just going to discuss its principle in details. Now, here I have put one note which I have already discussed, that crystalline state is at lower energy level compared to the polycrystalline state, and we want to minimize the energy. That means, on principle we are going to solve the minimization problem. Now, supposing that I have got one maximization problem, what you can do is we can convert it into minimization problem and solve it using simulated annealing. Now, let us see the working principle. Supposing that I have got one objective function, minimize y is a function of x, E x is the energy, and a capital X actually it indicates the collection of all the design variables. Supposing that I have got n number of design variables. So, capital X is nothing but a collection of small x 1, x 2 up to x n, and this is the range for the variable x is lying between x minimum and x maximum, and this is actually a unconstrained optimization problem, because here there are no functional constraint. Now, let us see how to solve this particular the minimization problem using the principle of simulated annealing. Now, step 1, we assume initial high temperature of molten metal, say T naught, and we select some initial random solution, say x naught, and the termination criteria is epsilon. That means, if the change in energy between the two consecutive iteration, if it becomes less than equals to epsilon, so we terminate the program and we say that it has reached that particular the optimal solution. And generally, we keep a very small value for this particular the epsilon. We set iteration number, so t equals to 0. Step 2, we calculate the temperature of t plus 1th iteration, and that is nothing but the 50% of the previous iteration temperature, that is t corresponding to t plus 1th iteration is nothing but 0.5 multiplied by t corresponding to the tth iteration. Capital T indicates temperature of molten metal, small t is the iteration number. So, we generate a candidate solution for t plus 1th iteration, that is capital X t plus 1. As I told, capital X carries information of all the small x values, that is the design variables, and this capital X t plus 1 are selected at random in the neighborhood of x t using the random number generator. Now, we will have to check whether this particular x t plus 1 should be accepted or not. Now, step 3, if the change in energy, that is delta E, is nothing but E corresponding to x t plus 1, x t plus 1 I have already selected at random. So, corresponding to that we try to find out the energy, and we try to find out energy with respect to x t, find out the difference. Now, if this particular difference, if it is less than 0, we accept x t plus 1 as the next solution and set t equals to t plus 1. So, we try to find out, so whether this particular E x t plus 1, whether it is found to be less than or greater than compared to E x t plus 1. Now, this is a minimization problem. So, if we find that E x t plus 1 is less than E x t, that is a better solution, and we select that particular x t plus 1 for the next iteration. Now, else we generate a random number r lying in the range of 0, 1, and we check this particular the condition. Now, supposing that the previous condition is not fulfilled, if it is not fulfilled, then x t plus 1 should not be selected as the next solution. Now, what we do is, if it is not selected through this particular checking, now what you will have to do is, so you will have to go for the next checking. That means, if the solution is not selected here, we just want to give another chance, and whether it can be accepted or not, that we are going to check. So, what we do? We generate a random number r lying in the range of 0 to 1, and if r is found to be e raised to the power minus delta E divided by t corresponding to t plus 1, then we accept this particular the solution, although it was not accepted previously. So, we just want to give one chance. Why do you use this type of expression? That I am going to discuss after some time. Now, if this particular condition holds good, we accept x t plus 1 as the next solution and set t equals to t plus 1. Else we reject x t plus 1 and set t equals to t, that means there is no improvement of the solution, and we go to step 2. Step 2 means we will have to come back here. So, we will have to reduce the temperature, generate what should be the possible solution, and then we go for the checking once again this. If it fulfills, we select if it fails here, we want to give another chance. If this particular condition holds good, we select even if it is rejected previously, and if we select this, then we go for the next iteration, and if it fails here, then we reject x t plus 1 and set t equals to t and go to step 2. So, this is actually your the principle. Now, actually we just want to check the termination condition. Step 4, if the mod value of the difference, that is E x t plus 1 minus E x t. So, this will be capital X t, here there is a small mistake here, this will be E capital X t. So, if this particular difference, the mod value of that, if it is found to be less than epsilon, and if t reaches a small value, we terminate the program. So, this is the way actually this particular algorithm works. This algorithm is very fast, and here there is no such operator like GA crossover mutation and that type of thing, and compared to GA, so it will be faster. Now, I am just going to check and I am just going to discuss why did I use this type of expression. So, we use this type of expression, and there is a valid reason behind that, and that I am just going to discuss. Now, to discuss that, actually I will have to take the help of the Boltzmann probability distribution. Now, according to this Boltzmann probability distribution, a system kept in thermal equilibrium at temperature T has its energy distributed probabilistically according to this. So, P E is nothing but exponential minus E divided by this k T. Now, here actually what happens, the system is in thermal equilibrium at temperature capital T, and its energy will be distributed probabilistically according to this particular the rule. Here this k is nothing but the Boltzmann constant, and in this simulated annealing what we do is, for simplicity we assign a numerical value that is equal to 1 to k. Now, in that case, so in our simulated annealing algorithm, so probability that NRG will be probability of energy distribution is nothing but exponential minus E divided by T. Now, let us see what does it mean. Now, if I take a higher value for this particular the T, so higher the value of this particular T, so lower will be E by T, because k is 1 here. So, higher the value of T, the lower will be E by T, and lower the value of this particular E by T. So, 1 divided by, so this exponential that particular E by T will be low, and that means 1 divided by that particular E raised to the power E by T will have the high value. Now, let us see how to find out. So, it is nothing but, so probability of energy is nothing but E raised to the power minus E divided by T. Now, here k has been considered as 1. So, as T increases, as T is high, so what will happen, your E by T will be small, That means, so what will happen is, if E by T is small, so this is nothing but 1 divided by E raised to the power E by T. So, E by T is small, means this particular amount is small. So, this probability value will be high. That means, at a high value of T, the probability will be high, So, once again let me repeat, at T increases or at high T, the probability of selecting the bad solution, that is probability of this energy will be actually high. So, if T is high, probability is high. On the other hand, if T is low, the probability is low, and this probability is actually in simulated annealing, the probability of selecting the bad solution. Now, if I just come back, now we can see that. So, this is the way actually this particular probability distribution has been considered. Now, if you see the distribution, as I told, when t is high, the probability of selecting the bad solution will be more, and with the iteration the t becomes low, the probability of selecting the bad solution will become small. It means that initially at the starting of the algorithm, there is a probability, high probability that bad solution will be selected, but with the number of iteration, the probability of selecting the bad solution should be low. That means, initially we allow more diversification in the algorithm, and with the iteration this particular the chance of diversification will be less. So, this is the way it will try to optimize, it will try to minimize that particular the function. So, this is the philosophy behind selecting this type of probability distribution according to Boltzmann probability distribution, and this particular thing has been copied in the simulated annealing. So, whatever I mentioned, the same thing I have written it here. At high temperature, the probability of selecting the bad solution is more. At low temperature, the probability of selecting the bad solution is less, and accordingly we have selected that particular your probability distribution. So, this is in short the working principle of a simulated annealing. So, it is very simple, much simpler compared to the genetic algorithm, and it is faster also. Now, to understand the working principle of this particular the algorithm simulated annealing, I am just going to solve one numerical example. It is very simple. Now, the objective function is to minimize y equals to E x, that is the energy corresponding to capital X, and that is nothing but the function of two variable x 1 and x 2, and that is equals to x 1 plus x 2 minus x 1 square minus x 2 square, subject to x 1 x 2 is lying between 0.5 and 0.0 and 5.0. So, this is the range for this particular the design variables, and this is once again one unconstrained optimization problem, and there is no functional constraint. So, what we do is we assume the initial temperature of molten metal, say T naught, say 3000 degree Kelvin, and initial random solution we can select lying within this particular range, that is x naught is 2.5, 2.5, that is small x 1 equals to 2.5 and small x 2 equals to 2.5, and this is the random initial solution, and the termination criteria epsilon is 0.001, and let us assume that the random numbers varying in the range of 0 to 1 are as follows, like 0.3, 0.8. These random numbers I am going to use in this particular the iterations. Okay. Now, let us see how does it work. Solution. So, the given T naught, then the initial temperature is 3000 degree Kelvin, and the initial random solution x naught is 2.5, 2.5, that is small x 1 is 2.5, small x 2 is 2.5. Now, value of the objective function corresponding to x naught, that is E x naught, is nothing but minus 7.5. Now, how to find out this? It is very simple. So, what you do is you substitute in this particular expression of the objective function, you substitute the values of small x 1, x 2. So, we will be getting the numerical value, and that numerical value is nothing but minus 7.5. Now, what you do is we go for iteration 1. So, iteration 1, we find out T 1, that is 50% of T naught, that is 50% of 3000 degree Kelvin, that is nothing but 1500 degree Kelvin, corresponding to the random numbers 0.3 and 0.8. If you remember, so we generated a few random numbers here 0.3, 0.8, 0.7, like this. So, I am just going to use 0.3 and 0.8. Now, corresponding to 3 is 0.3 and 0.8. The random numbers corresponding to this, the real values of capital X 1, that is nothing but the collection of small x 1 and x 2 will be as follows. Now, let me discuss how to find out this. Now, the random number which you have considered is 0.3 and 0.8. Now, what you do is the range for the variable. So, x 1 x 2 if you remember is lying between 0.0 and 5.0. So, the range is 5. So, what you do is 0.3 multiplied by the range, that is 5.0. So, this is nothing but 1.5, and corresponding to this 0.8, it is 0.8 multiplied by the range, that is nothing but 4.0. So, I can find out. So, this is nothing but value for small x 1 and this is the value for small x 2. Actually, the rule, let me write it here. Supposing that I know the random number, I know the range. The rule is as follows. If I want to find out the real value, for example, x, the real value is nothing but x minimum plus the random number r multiplied by your x maximum minus x minimum. Now, here in this particular problem, your x minimum is 0, okay, but this is actually the rule how to find out the real value. Here x minimum is 0 and random number is 0.3, x max is 5, x min is 0. So, I can find out this real value. So, this is the way actually we can calculate actually this 1.5 and 4.0. And once you have got this 1.5 and 4.0, you substitute in the expression of the objective function and then you will be getting the function value. So, we will be getting the function value, that is E x 1 is minus 12.75. Now, we compare E x 1 with E x 0. Now, E x 0 was how much? Minus 7.5 and E x 1 is minus 12.75, and if I compare, we can find out that E x 1 is less than E x 0. That means, E x 1 is a better solution compared to your this thing. So, what we do is we select x 1 as the next point, because here E x 0, E x 1 is found to be less than E x 0 and we are solving the minimization problem. So, x 1 is a better solution compared to x 0. So, we select x 1 as the next point, and then we can find out the change in energy delta E is nothing but the mod value of E x 1 minus E x 0, and here it is coming to be equal to 5.25, and as this particular change in energy is found to be greater than epsilon, that is the termination criteria, we go to the next iteration. Then iteration 2. So, T 2 is 50% of T 1. So, 50% of 1500 is 750 degree Kelvin, and corresponding to the random number 0.7 and 0.6. So, we can find out x 2 is 3.5, 3.0, and I can find out the function value is nothing but minus 14.75. Now, if I compare E x 2 and E x 1, so E x 2 is found to be less than E x 1. So, we select x 2 as the next point. Change in energy delta E is found to be 2.0, and as delta E is found to be greater than epsilon, we go to the next iteration. This should be delta. Now, iteration 3. So, we go for T 3, that is 50% of T 2, that is 375 degree Kelvin, and corresponding to the random number 0.2 and 0.5, we get x 3, that is 1.0, 2.5, and we find out the function value, that is minus 3.75. But here if we compare E x 3 and E x 2, E x 3 is found to be greater than E x 2. So, we cannot select x 3 as the next point now, and we will have to go for the further checking, the next checking. What is that checking? The checking is like this. So, which I have already discussed. So, what we will have to do is, we will have to find out the exponential minus delta E by T 3. Now, how much is delta 3? Delta E is a mod value of the difference between E x 3 and E x 2, that is 11.0, and T 3 is your, we know the value of T 3. So, that is nothing but your 375. So, if you use T 3 as 375 and delta is 11.0. So, I will be getting 0.97, but the next random number is 0.6. Okay. So, this random number r is found to be less than 0.97. So, we accept x 3 as the next point, although it was not accepted previously. Now, according to this particular checking, so I am just going to accept this particular x 3 as the next point. This procedure is continued till it reaches the termination criteria. At that particular termination criteria, that is change in energy, its mod value should be less than that epsilon, that is the termination value. Okay. And if it fulfills, we say that the algorithm has reached that particular level, and the solution which we are getting is the optimal solution, that is the minimum solution of the objective function. Thank you.